Okay, welcome everyone to the latest in the DARA e-seminar series. It's a real privilege today to welcome Professor Peter Wilkinson to give the latest of these seminars. Peter will be known to many of you, I think, within the DARA family. He's been in this whole endeavor from the start, and many of you will have. The Kenyans will all be very familiar with Peter, as he delivers the Unit 1 training in Kenya. And when we do get back face to face, the Ghanaians and the Kenyans will get the pleasure of Peter coming along to help with the practical training in Ghana, hopefully around Easter next year. Peter's had a very illustrious career in radio astronomy. Been a real stalwart of the Jodrell Bank Observatory at the University of Manchester, and has real tower of strength across a wide range of topics in radio astronomy, observation, as well as you'll see today, more on the practical side of building instrumentation and on that side of radio astronomy. And it's that he's going to focus on today. So for a while within the DARA project, we've been hoping to be able to get some sort of hands-on radio astronomy kit out to each of the partner countries, so that groups and especially universities, undergraduates can really get to grips with doing something practical, do some experiments with kit that they can sort of build and put together themselves. It was, Peter stepped forward to sort of take charge of that side of things. And finally today, that's what he's going to tell us about. So this is the first of a kind of a two-part e-seminar. So today he's going to sort of run through, how this kit works. And then there'll be a follow-up, more of a sort of practical demonstration, I think, of how the kit works. So without further ado, I'll hand over to Peter.
So hello everybody, can everybody see my screen?
Not yet, I think.
Well, where was the, I haven't got a...
Okay, well...
share screen.
Yeah, while Peter's sharing screen, again, if you think of questions as you go along, please put them in the Q&A box, not the chat box, and we'll take the questions at the end. Yep, we can see that now. Yep.
All right. So hello everybody. Welcome. And as Melvin's just said, this is a slightly different type of seminar. And I'm going to be telling you about, in a two-stage process, what I've been developing for people to have hands-on experience with radio astronomy in universities across Africa, particularly, of course, in the DARA countries. So today is number one of a two-part series, both of which are under the title Observing the Milky Way with a Tabletop Radio Telescope. So the overview is this is two seminars, and my aim here is to make the tabletop radio telescope, the TTRT, usable. And I'm assuming there might be limited supervision, limited expertise in these various places. We're going to put 20 copies of which out of the TTRT across Africa in 2021. The main point of these videos is that you should be able to, or students, many of them will be the DARA students, but of course other people who might become DARA students will get access to this instrument. The idea is to build a confidence building pathway. We've seen these two videos first, so when presented with the kit and the book, it won't be such a big shock. You'll say, yes, I understand that, and I can follow the book in more detail and use the kit. So today, number one is, this is the astronomy part of it, introducing the principles of the 21 centimeter hydrogen ion observations, and showing how astronomers 60 years ago were able to show the Milky Way has spiral arms. a few recent results on the Milky Way and nearby galaxies. And at the end, I'm going to, since it's not a research seminar, but hopefully a very educational one, leave you with a few exercises to try, which are downloaded onto the DARA site. So we'll go through them quickly at the end of this talk, but you'll be able to download the PDF and have a go at them. So let's start. The SKA has been foremost in my thoughts for almost...
Sorry, Peter. The sound is a little bit scratchy. I don't know if... Are you using a microphone or...?
I'm not.
Okay. I don't know.
Can you hear me now? He shouldn't have been any different from before.
No.
Can you hear that?
That sounds a bit better now. I don't know if there was like just paper rustling or something nearby. I don't know. But that sounds better now anyway.
Okay, I'll move that microphone out of the way. That loudspeaker.
Yeah,
how's that?
That sounds good. Thanks.
Okay, sorry for that, everybody. But so just to repeat, this is a two-part seminar then. Number one is introducing the principles of hydrogen observations and leaving you with a couple of exercises to try at the end. This isn't a research seminar, but hopefully an educational one. So the SKA has been much in my mind for almost, since 1985. I first had thoughts about it. Wrote this paper called The Hydrogen Array in 1990 and published in 1991, when I conceived of it as something which is almost 100 times bigger than the VLA, the principal aim of which was to study hydrogen at cosmological distances. And at least in the phase one, we'll be starting in South Africa, at least phase one mid, towards the end of this decade. So I've had this idea, this thought of allowing students to see the hydrogen, obviously on a rather smaller scale than the SKA. And this is the tabletop radio telescope. As you can see here on the left-hand side, can everybody see my cursor?
Yeah, we can see your cursor, Peter.
Okay, very good.
The sound was getting bad again, just a little bit. I think maybe if you're a bit further away from the screen, it seems to be a little bit better, as long as you can still see the screen.
Oh, absolutely. Sorry. How's that?
That's a bit better, I think.
Okay, I'm sorry about that sound. I think we had a practice beforehand. It seemed okay. So here's the kit on the tabletop in my garden. Here's the antenna, which is a tin can with a horn on the end of it, which you can buy very cheaply. A box with electronics, the little dongle as a detector, and of course that's what will be supplied, that lot, and the laptop you have to supply. So it's going to be a chance for you to detect hydrogen for yourself and to see the rotation of the Milky Way. And actually seeing hydrogen line while you're doing it is always a thrill, I've found, to other students who've pioneered this experiment. And even if you don't get to use it yourself, because you're former DARA students, you'll still get to see videos of the telescope in action at seminar number 2. Let's first of all just think why radio astronomy, and why I've been so keen on radio astronomy for so many years, is important. Why is it important? Well, first of all, we have the cosmic microwave background, of course, which is the earliest radiation accessible to us and is the cornerstone of modern cosmology. Secondly, and it's important for us today, radio waves penetrate dust and gas, which obscure other wavelengths. So that's enabled us in our own galaxy to study a lot of the processes of star formation and evolution, astrochemistry in cold clouds, star and planet formation in dusty disks, and the ionized atmospheres of stars and the interstellar plasma. And more generally, radio astronomy provides access to hydrogen, which is the fundamental element, which is a tracer of many processes in the universe, particularly gravitational tracer, high energy processes in accretion onto black holes and quasars, cosmic magnetic fields by the polarization, Pulsars are the most accurate clocks in the universe, enables us to test general relativity to high accuracy. And of course, the highest resolution images in all astronomy with VLBI, most obviously with the Event Horizon Telescope just recently showing the shadow of a black hole in the galaxy Virgo A or M87. So today we're going to be concentrating on two bits of this. We're going to be using radio waves to penetrate the dust and gas, and we're going to be observing hydrogen. Now, hydrogen is by far the most abundant chemical element in the universe. It's about 75% of the mass. Most of it's locked up in stars, but there's quite a lot between the stars and between galaxies. And a significant fraction of that is in the form of neutral atoms. And neutral atoms, the astronomical nomenclature for neutral atoms is the Roman numeral 1. So it's called H1. Or atomic hydrogen, neutral hydrogen, H1. They're all the same thing. And of course, it emits a radio spectral line whose wavelength is very accurately known at 21 centimeters, just over 21 centimeters. Many of you will know that the line arises from a so-called spin flip transition. The spin of the proton and the electron can either point in the same direction or in opposite directions. And although it's not obvious, because the electron has a negative charge and the proton has a positive charge, the spins are aligned in the high energy state and misaligned in the low energy state. It's not obvious if you have them pictured as bar magnets, but if you picture them as rotating currents which are overlapped in a quantum mechanical sense, this is the way around it is. There is a nice, I can tell you at the end, there's a very nice paper which explains this in quantum mechanical, also semi-classical terms. Anyway, the main point is there is a transition whose frequency is very accurately known. The problem with hydrogen is that individual atoms sit around for 11 million years before deciding to do anything, typically. And so the emissivity of a clump of hydrogen atoms is very low. However, there's an awful lot of hydrogen in the universe. So as it turns out, hydrogen in our galaxy can be observed with very simple apparatus, like the tabletop radio telescope. To look at it across the universe, you need something like the square kilometer array. Now, what we're trying to do is to meet the challenge of galactic structure. Can I just move that out of the way? Our galaxy we live in, of course, is the Milky Way. Here's a beautiful picture of the Milky Way taken over Kenya, as it turns out. It's an assemblage of over 10 to 11 stars with gas and dust, particularly dust, held together, of course, by their mutual gravitational attraction. So its internal structure depends on the form of the gravitational potential, in other words, the mass distribution, which is quite complicated and has, of course, been influenced by mergers in the past with other smaller galaxies. And that merger process is actually of great interest today. We won't be talking about that, but we're trying to find out the mass distribution and the shape of the stars, the morphology, if you like, of the Milky Way. Now, we've long known that the Milky Way has a disk-like structure. Now, I'm not going to have time to explain that, but I would advise you strongly, as I've advised people in Unit 1 in Kenya, to Google the series of videos called Crash Course Astronomy. They're very good. They're a bite-sized chunk, usually about 9 or 10 minutes. And the one, number 37 on the Milky Way, is a very good introduction to a background to some of what we're talking about in this seminar. So please look at Crash Course Astronomy number 37. However, and this is the point, establishing the distribution of stars and gas inside our galaxy is hard because we're living within it. And as you can see on this picture here with the dust clouds here, dust often obscures the view, and certainly obscures the view towards the center of our galaxy. So what to do? Well, we're going to use gas and dust So we're going to use the transparency of radio waves to dust to diagnose what the shape of our galaxy is. But first, before we do that, this is an optical picture again. We must make our first encounter with a new coordinate system, which we're going to talk about a lot more in E-Seminar 2, because when we're looking at the sky, we want to observe in not just Earth-based coordinates, but also in galactic coordinates. And here we see the Milky Way arranged differently to the previous slide. This is real life over Kenya. What you do is you rearrange everything into galactic coordinates, as I've marked latitude and longitude. The galactic center is here, and at the bottom here are the Magellanic Clouds, which are dwarf galaxies spatially separated from us, but in orbit around the Milky Way. So, and this whole rugby ball shape is projecting the whole 4 pi radians of the sky onto a flat plane. So astronomers often show it in this form: the plane of the Milky Way along the middle, the galactic pole, North Pole here, galactic South Pole here, galactic latitude up the side. So here is hydrogen in the Milky Way. This was optical light, the stars obscured by dust. Here's hydrogen mapped with large radio telescopes. And here you can see the galactic plane, but now we don't see dust. If you notice, the hydrogen, which is the yellow, is very strongly concentrated towards the plane of our galaxy. Here's the center again. Here are the 2 poles. The intensity is much stronger along the plane of our galaxy. And as you go away from the plane of our galaxy, you see much less hydrogen. This has been mapped with the so-called H1 4 pi collaboration of telescopes around the world. H1, we've explained, 4 pi for 4 pi steradians. They map the whole sky in hydrogen. Now, the beauty of hydrogen is that you can get some quantitative information about it immediately via the Doppler shift. Now, many of you will know about this. The non-relativistic Doppler formula, because the speeds are low, is that the change in frequency observed compared to the emitted frequency is just the speed divided by the velocity of light. The emitted frequency is 1420.4 megahertz, the so-called rest frequency. V here is the relative velocity along the line of sight. Across the line of sight, transverse, we see no effect non-relativistically. It's just the line of sight velocity away from us. And it's the relative velocity, because we are moving as well as the source, and that's called the radial velocity. For a shift of about 100 kilohertz, 0.1 megahertz, which might be a low shift, the velocity will be about 21 kilometers per second. So we sometimes plot the spectrum in terms of frequency, and often we translate it into a radial velocity in terms of kilometers per second. And by convention, if the observing frequency is less than the emitted frequency, then the gas is moving away from us, and that velocity is called positive. You might say it's been redshifted. Lower frequency, longer wavelength. If the observing frequency is higher, then the gas is moving towards us, and that is called blue shifted. So to make this clear, here's structure in the 21 centimeter spectrum. Here's a radio telescope, and it's also moving because the sun and the earth are moving. Here's a hydrogen cloud, and I've drawn it. It's got some bulk motion away from us, but we only see the projection along the line of sight. So the line here would be shifted away from the rest frequency by a certain amount. Here it's moving at 100 kilometers per second, just about. It's about 500 kilohertz shift. But then the cloud has motions within it. There are random motions within the cloud. So the line is not only shifted away from zero, it's also broadened due to the internal motions of the cloud. So when we actually observe with a radio telescope, we point a telescope at the sky, And because the radio waves go through the dust, you see all the way through the galaxy. Here's the beam of the telescope. You see pointing in that direction, but you see hydrogen from that direction, and all points in between. So the result is a composite spectrum with multiple peaks. Sometimes you see more gas from these, turns out, spiral arms. So you see some coming towards you, some coming away from you, and some with no relative velocity. So you see some sort of complicated spectrum like that. Now, let's look again at the big picture. Here we're going back to this H14 pi we've seen before. We saw a few slides back, but this has now been encoded in color with respect to velocity. And as you point the reception beam around the plane, you find that gas is sometimes coming towards us and sometimes moving away from us. And here they've got the positive radial velocities going away from us in green, and the negative radial velocities coming towards us in blue and purple. So as you can see, as you go around, there are regions which are all green, all purple. So there are clearly ordered gas motions within the galaxy. But how do you make sense of them? Note that these are, again, the Magellanic clouds. They're well away from the galaxy and have different velocities, so they come up at different colors. They're the same things we saw optically a bit earlier on. So how do we make sense of galactic motions? Well, here's a spectrum again. Sometimes you can plot it in terms of frequency. Then you can easily turn it into radial velocity just using the Doppler shift formula. So getting the frequencies of these clouds at different peaks here is relatively easy. In fact, it's very easy. But getting the distances is more difficult. But first, let's jump into the problem, assume that we can work out the distances and see if we can, what we might observe. So we know that actually the Milky Way is rotating. How might it be rotating? What form might that rotation be? Well, if the Milky Way was completely dominated by the black hole at the center, we know there's a black hole at the center. If it was dominated by the black hole and the stars around it, it would be just like the sun in the solar system, which would be so-called Keplerian rotation. And all of this can be done with Newtonian gravity. The force on a particle is g, Newton's constant, times the mass within a certain radius, times the mass of the object over r squared. That equals mass times acceleration. Motion in a circle, acceleration towards the center, is mv squared over r. So if you had everything dominated at the center, and here we start up with 3 clouds, this on circular orbits around the galactic center, if they all start in line, then if they were moving like the solar system, then the inner ones would move faster and would get ahead of the outer ones. And the velocity as a function of distance would look like this. And if you just employ this equation here, where m is just a point at the center, the velocity would go as 1 over the square root of r, sorry. So at greater distances, velocities would be lower. At greater distances, the velocity is lower, higher towards the middle. That's not what is observed. Well, what else might it be doing? The opposite might be observing as rotating as a solid body, like a disk, like a record or a CD disc, or just a flat discus going around, everything connected together. So they start in a line, these objects, and they stay in a line. And that would mean, of course, that the outer ones are moving faster because they have further to go, and to keep up in a line, they have to be moving faster. That's called solid body rotation. And the velocity as a function of distance would just be proportional to r. If you solve the, and this is all explained rather more in the instruction booklet, so don't expect to follow this all instantly. The mass inside a radius r would have to be proportional to r cubed. It would be, the mass would have to be distributed within the galaxy, and its mass as a function of r would have to go as r cubed. That would mean, if this is true, then at greater distances from the center, the velocities would be higher, and that's not what is observed. Well, what is observed then? Oh, I missed a bit out at the bottom. In fact, that is true very close to the center of the galaxy. We'll come back to that later. Well, how is the Milky Way rotating? Well, it turns out it's rotating in a rather unexpected fashion. There is almost no difference, as well away from the galactic center, up here, these circular orbits. They're all rotating at the same speed. So the speed of that one there, the speed of that one there, the speed of that one there, all the same. So what we call is the flat rotation curve. The distance from the center against orbital velocity is pretty constant. What that means is the ones outside slowly fall behind the ones inside. So these are the circular orbits around the galactic center. So these outer ones slowly fall behind the inner ones. This is what is observed, except close to the center. We say the galaxy has a flat rotation curve. And if you solve the Newtonian gravity equations, it must be the mass inside a radius r has to be proportional to r. So let's, with those ideas in mind, let's try and build a geometrical model. So astronomers have used an idealized model, assuming stars and gas move in circular orbits about the galactic center. And based on this, it's possible to determine distances in certain directions from the hydrogen line observations alone. And one of the exercises will go through this. And these have helped to establish that we do have a flat rotation curve. And with that curve, you can estimate other cloud distances. We'll go into this. There are some ambiguities, but we can overcome those to some extent and begin to uncover the overall structure of the galaxies. This is one of the first triumphs of radio astronomy in the first 15 years. So to make this clearer, here's the sun. I've put a giant black hole at the galactic center. Of course, it's nothing like as big as that, but it's in a circular orbit around the galactic center. Here, again, assuming our final result, you see a lovely artist's impression of the Milky Way looking down on it. Of course, we can't look down on it. We're looking from the inside. Now, these spiral arms are in fact not fixed structures. They are dynamic structures, and the sun goes through the spiral arms. And again, if you want to see an explanation for that, look at the Crash Course Astronomy number 37, which explains the dynamical aspect in simple terms of the spiral arms of our galaxy. What we're trying to find out is, where are the spiral arms? This is a lovely picture in a recent Scientific American. Keep going the wrong way. So there's going to be a few slides here which now explain this geometrical model. I'm not expecting you to follow this in quick detail. Those of you who will do the experiment will see it all explained in the booklet, but this is me going through it to give students confidence that they can follow the booklet more easily. So here's the first picture. Here's the galactic center, and the sun is moving around it at a distance r0 and a velocity v0. So its angular velocity about the galactic center is how many degrees or how many radians it goes per certain time is v0 over r0. But what we're concentrating on is just its speed and its distance. I was going the wrong way. So now this picture looks a bit more complicated, but this is the same orbit we had before. But now I've got an inner orbit with a gas cloud on it. The sun's going at v0, and the gas cloud is going around in a circular orbit at a distance r from the galactic center and a distance little r from us. I've now put on some galactic longitudes pointing towards the galactic center, longitude 0, pointing in the opposite direction, the so-called anti-center, 180 degrees. And so longitude with respect to the center is here, and this might be longitude, say, 35 degrees. And it goes around 90, 180, 270, 360, back to 0. Now, we've got to work out the radial velocity of this cloud. So that's the difference between the projection of the Earth's velocity along this line and the cloud's velocity are along this line. This blue line is the line of sight. And it's easy to work out. Here's this angle delta here. The radial velocity of a cloud with respect to the sun is given by this equation down here. Can everybody see that equation? I hope they can, because on my picture it's blanked by the videos of the speaker. It makes it a bit difficult for me to. Right, that's better. Oh dear, sorry. Right. Let's go back to that. Here's the equation. So here's the equation. As we, you can use a little formula here. Again, it'll be explained in the booklet. To get the equation we'll use a lot, that the radial velocity, which is the projection of the Earth's velocity along this blue line, with respect to the cloud's velocity with respect to this blue line, is radial velocity is the cloud's velocity times the ratio of the radii of the distances times the sine of the longitude minus the Earth's velocity times the sine of the longitude. So it's a very simple formula. Now, a very important point. Let's look at the cloud on a different part of this orbit. It's the same sun, same inner orbit, but at this particular point, this particular longitude where it grazes the orbit, the so-called tangent point, if you observe at that longitude, the maximum velocity you will ever see is from clouds at the tangent point, because there the cloud is pointing directly away from us. Do you see that? Here's us, we project our velocity onto this line, but the cloud's velocity is on that line. So that's so-called the maximum radial velocity. And it's at a tangent point, which means that you will know exactly where it is. It's always on the orbit which is closest to the galactic center for that particular longitude. Again, this will all be explained in the booklet, but it's interesting to see. This is exactly what astronomers, radio astronomers, found out or invented, this ingenious ideas in the 1950s when they first started observing the galaxy with hydrogen. Now, another cloud around here, it's on the same orbit. Look, looks complicated, but this is a cloud on the same orbit as that one at the tangent point. It's also going around at velocity v. It's further away from us, but it will lie at a different longitude here compared to here. And so it will have a reduced component of its velocity along the line of sight. This one's got this whole velocity component here. This one's just got this purple velocity component along the line of sight, and hence it's lower. The maximum velocity you'll always see is at this point t, at the tangent point. You'll use that in the exercises. A few other things we'll come to during the when you start observing the sky with the tabletop radio telescope. A few things that astronomers diagnose the sky, the positions in the sky. We have galactic quadrants, so-called, and the solar circle. Here, these are just orbits around the galaxy. The sun orbits at a particular distance. We'll talk about that later. It's in green. Here's an inner orbit here. So this is called the solar circle. Here we have 0 degrees, 90 degrees, 180 degrees, 270 degrees. These are galactic coordinates with respect to the sun. We'll be going more, we've already seen a little bit about galactic coordinates. We'll go more into it in E-Seminar 2, when you actually have to point the telescope at particular galactic coordinates. Don't worry, it's all done from you, all done for you in a little app that you can use. Anyway, the main point, the solar circle here. Whoops. Sorry, I keep going the wrong way. So quadrant 1 is down in the bottom right-hand corner. Quadrant 2 is up there. quadrant 3 is here, and quadrant 4 is here. So galactic astronomers refer to these quadrants and to the solar circle. But they also refer to points outside the solar circle. Here's an orbit outside the sun, because the sun is only partway out towards the center, away from the center. And if I mark everything inside the sun's orbit in green, that's called the inner galaxy. And everything outside the sun's orbit is called the outer galaxy. If you notice that clouds inside, clouds in quadrants 2 and 3 out here are always outside, with respect to us, outside the solar circle. So outside us. Clouds in these quadrants here are can be either inside or outside the solar circle. So notice, by the way, that everything is with respect to the sun. We're not measuring galactic coordinates with respect to the galactic center. It's with respect to us. So I'm making this more clear. Here's the galaxy again. Here's the solar circle. Here's the inner galaxy here. Here's the outer galaxy. And here are the quadrants. So galactic astronomers use this nomenclature all the time. Now, we're going to observe this galaxy from the inside. Here's the quadrants and the inner galaxy and the outer galaxy. And remembering it's got differential rotation. Here's this picture we had earlier. So here I've now drawn the solar circle in green again, and we've got clouds outside the sun in the outer galaxy, and clouds inside the sun and the inner galaxy. And notice, because they're going around at the same speed, clouds on the inner galaxy tend to get ahead of us. They're going faster. Well, they're not going faster. They've got less, they're going at the same speed, but they've got less far to travel. So they move around their circle, their orbit faster. Clouds away from us, moving at the same speed, but they've got further to travel. So they fall behind us. And as a result of that, and I won't go into this, it's pretty obvious when you think about it, outside the solar circle, clouds are approaching us in quadrant 1 and 2. Down here, quadrant 1 and 2, they're approaching. The sun is catching them up. We're going faster than them. So the radial velocity is redshifted. They're sorry, blue shifted. We're catching them up. In this part here, we're racing ahead of them. So we tend to leave them behind and they are receding from us. On the inner galaxy, they're moving faster than us inside here. So they're moving away from us. The sun's falling behind in these quadrants here, this quadrant in the galaxy, and the sun is catching them. They're catching the sun up. They're overtaking us in this part. That's all because of this differential motion, that the velocities are much the same as a function of distance, and therefore further out, they've got further to go. They move relative to us more slowly, and inside relative to us more quickly. So this is the overall picture, and I'm just putting this up again, which we saw before. When you look around the galactic plane, this is looking down from above. We can't do that. Inside, you see these regions where it's receding, approaching, sorry, receding, approaching, approaching, receding. It's because of this picture that I've been sketching together. And astronomers realized this in the 1950s. This is a 2010s picture, but they realized this even with much simpler apparatus in the 1950s. We're able to make great progress about studying the galaxy. This looks complicated, but along the line of sight then, so we've got the sun on its solar orbit, clouds on inner orbits, and I've drawn 1, 2, 3, 4, 1, actually 2, 3, 4, and a cloud, a transition, the transit point, the tangent point. And I've left all these approaching recedings in. So if you look along at that particular point in the galactic latitude here, cloud 1 would appear here, but also cloud 2 would appear here. It turns out there's an ambiguity because the projections of the velocity at that point and that point here are the same. So you can't tell whether clouds 1 and 2 are at the same, at different, can't tell the distance to them. At the tangent point, you see the maximum. And this particular quadrant, it will be receding from us. Number 3 here on the solar orbit is not moving with respect to us, so we see it at the same rest frequency. And number 4 here is outside as we're catching that up, and so we see it approaching. So commenting again, there is this near-far ambiguity here. You can't tell at a particular velocity whether it's away, a long distance away from us or close to us. But you can tell that point there unambiguously. And outside the sun's orbit, you don't have this ambiguity. And as long as you've got a rotation curve, you can tell the distance. Anyway, by this means, we made the first map of the Milky Way in 1958, or we did. These guys here, famous radio astronomers, which showed that the Earth, the basic structure of the Milky Way has these spiral arm-like structures. This bit of the sky they couldn't observe with their telescopes at the time. The basic spiral arm structure is visible. This was done in 1958. In addition, the hydrogen distribution is a bit complicated, as we'll see in a minute. So, summary so far. The sun's located partway out from the galactic center, and in any given direction, the observed hydrogen line spectrum is the combination of the emission from all distances through the galaxy and within the angular reception beam of the antenna. And as a result of differential rotation, emitting clouds have different radial velocities. And the observed spectra usually show peaks, revealing concentrations of hydrogen at particular radial velocities. These are the spiral arms. In fact, over 60 years ago, such observations interpreted with the circular rotation model I've just sketched in, and which those of you who get hold of the actual apparatus will see it explained in more detail there. It was those observations and that model, simple model, which gave rise to that previous picture, showed that our galaxy possesses spiral arms. And a short video, which I'm going to show you just now, shows a beautiful set of observations with a 3.3 meter dish in a back garden in France. Now, I want to hopefully this should work now. Our galaxy at 21 centimeters. Made with a dish in a back garden in France, a very nice little dish. 3.3 meter dish. Here you see his feed apparatus. And he's going to show you now what happens as you point the beam around through the galaxy, and you see different spectra. So he's scanning around the galactic plane, and you see how the various hydrogen spectra change as you move around the galactic plane. I'll just let this continue. It goes on for about another 30 seconds or so. This is a very nice piece of kit that somebody's put together in their back garden in France. A very professional set of observations. It's going all the way around to the best, to what we can see in France. And you can plot it in a particular way like this. I won't explain that. But what he's done also is to reconstruct the galaxy structure to what he called an XY map, which is, and that is essentially his version of what the Dutch and Australian radio astronomers did in the 1960s. Oops. Uh-oh, what have I done? Can you still see this, Melvin?
Yep, you're okay. Keep going. You're back on the slideshow, I think.
Okay. So that's low resolution. That's very nice apparatus, but we can't make anything as complicated as that for most universities. I just want to show you a few pictures of high resolution experiments. These are made with modern interferometers. On the left is an optical picture of a well-known galaxy M101. Oops. And on the right is the hydrogen picture of it. A couple of things to note. That the hydrogen structure is pretty messy, so but you can see the spiral arms, and also that the hydrogen structure is much bigger than the optical structure. See an example over here. It's dark, but here there's plenty of hydrogen, and that's absolutely typical. When you observe a galaxy with sensitive hydrogen line radio telescopes, you see that there is matter, which is helpful for diagnosing the matter distribution a long way out. Here's another galaxy which happens to be inclined to us, and therefore you can actually see the Doppler shifts. Remember, if it's face on, you can't see the Doppler shifts because everything's moving across the line of sight. If it's at an angle, you can see the Doppler shifts. Here's the optical galaxy. Because it's at an angle to the line of sight, you have some component, and here the gas is moving towards us, and here the gas is moving away from us. So you can see this overall rotation of this galaxy. And many studies of galaxies have been done like that over the course of history. The SKA, I think one of the exciting things the SKA will be able to do that in much more detail in some nearby galaxies. Although the SKA was invented, well not invented, one of the reasons was to look at cosmological hydrogen. I think there's going to be quite a lot of surprises from actually galaxies studied in detail in very high sensitivity.
Sound's going off a little bit again, Peter. If you can, I think if you can stay away from the screen a bit further again, that'd be good.
Okay. Now, another way you can pick out spiral arms, which we won't be doing, this isn't the TTRT, but it's radio astronomy. You can pick out spiral arms in the Milky Way with VLBI. One of the great advantages of VLBI is that you can measure the trigonometrical parallax. Excuse me, I take a thing. Which is how a nearby object would move with respect to the background objects, just because the Earth is moving around the Sun, as illustrated in this picture. Over the course of the year, a star will move, or a maser in this case, will move backwards and forwards with respect to distant objects, quasars typically, because the Earth is moving around the Sun. And because VLBI can measure positional changes to extraordinary accuracy, 2 times 10 to the minus 5 arc seconds, that's 20 microarc seconds, which is the size of a large coin at distance to the moon. So if one of the astronauts put a coin down the surface of the moon, that will be about 10 microarc seconds across. These accuracies are just a little bit bigger than that. So they're extraordinary accuracies. So you can actually measure distances and measure positions. And as a result of that, if you look at this picture here, this is again looking down from the top of our galaxy, and they measured the positions of various masers. These are different colors here, blue, green, purple, pale blue, and they've found that the sun is in fact in the middle of the galaxy in fact has 4 spiral arms, because they can get the distances very accurately, which you can't do with hydrogen observations so accurately as here you can. So we know we're in a spiral arm galaxy. This is observations just done in the last few years. They've also been able to find that something which is very difficult to establish because we're sitting in the middle of the whole business, that the distance to the galactic center is closely 8,150 parsecs, nearly 27,000 light years, and that we're moving around the galactic center at a speed of 236 kilometers per second from these very, very super precise VLBI observations published just less than a year ago. Our orbital period around the center of galaxies is about 212 million Earth years, which is just when the dinosaurs, 212 million Earth years ago, was just when the dinosaurs were getting going on the Earth. So the galaxy has only rotated around about 50 times since it was actually formed early on in the universe. So everything happens at a very stately pace. So back to hydrogen and single telescopes now. That's going back to the TTRT. The TTRT has too low an angular resolution to do what that very nice little video showed. That show was a beam of about 5 degrees or better. But, so we won't see the spectra we see won't be as clean as that, but they can clearly show the overall rotation of the Milky Way as you point to different latitudes, and we can explore how rapidly the hydrogen falls off as a function of galactic latitude. And we'll do that in eSeminar 2. But to complement this, these spectra, the instruction script contains a set of high resolution spectra taken with large radio telescopes like the H14Pi type. And with these, you can determine the rotation curve of the inner galaxy using the tangent point method. So I've supplied some professional spectra to complement the spectra you'll take with the TTRT. We'll quickly look at these. I won't go through them in detail because it's on the web, and you can download this as a PDF. So what I've supplied are spectra in different quadrant 1, and here they're at latitude 20, 30, 40, 50, 60, 70. And I've plotted on them, to make it easy for you, the maximum velocity you should lose. The radial velocity along the bottom is in hundreds of kilometers per second. In kilometers per second, that's 100. So that's a receding of 100 kilometers per second. And all you have to do is actually look on there what you think is the velocity. And in this particular quadrant, it's the maximum radial velocity at longitude 40, looks to me about 90, maybe 95 kilometers per second. And I put lines on to help you on the other ones. In quadrant 4, they're all approaching. And I've again marked to help you what the radial velocities are that you should use. So in each of the profiles, the dotted lines mark an estimate of the maximum velocity. And we showed you what the equations are. The radius for that particular velocity at the tangent point is just the Earth's radius times the sine of the longitude, and you're given that. And v is the maximum radial velocity, that's the dotted lines, times the Earth's velocity times sine of longitude. So you're given R0, you're given V0, and you can calculate R, just by that means, and you can calculate V with that equation. So what you can do is, I did it in a little table here, but I've actually given you, to make sure you're on the right track, the first set of calculations. Here's sine of the longitude, here's the distance, here's the maximum velocity I've seen at that longitude from the plots, here's kilometers per second, and here is V. And in the other quadrant, things are negative because they're receding, or approaching rather. So keep the sign, and you can fill in these things here and plot the rotation curve. Exercise 1b is to explain that spectrum, which is taken in that direction. I've just put this on to remind you of the configuration. So we're now looking at a cloud in this direction, L equals 180 degrees. Why does its radial velocity look like that? You can calculate the mass of the inner galaxy from your rotation curve, from the maximum velocity you see in your rotation curve and the maximum distance. You can calculate the mass, and the trick here is to give the answer in solar masses. So you have to get the units right. But that's the equation you use, and you've got R, you've got V, and you've got, you know what G is. Finally, we must talk about the dark matter halo in the galaxy. And you should have found that the rotation curve is flat or even slightly rising with R. So we've got a flat rotation curve. We know that the Keplerian expectation that the mass of the galaxy concentrated in the center should show a curve like this, but in fact it shows a curve like this. So there must be something compensating. And if you take that away from that, you see something like this, and this is thought to be due to the dark matter halo, which extends out far beyond the stars. And in fact, many of you will have seen this plot, which Melvin uses in, and I use in his Unit 1 exercises. This is in fact taken from a very classic paper, not observed with radio astronomy, but in 1978, which shows the rotation curves of galaxies a long way out. Note that near the center, it's differently. That's a so-called solid body rotation. But here we're concentrating on pretty well flat. And it was this observation which convinced people that there must be something over and above the stars. And it was the inferred dark matter halo. The current estimate of the Milky Way's total mass, including dark matter, is at least 10 to the 12 solar masses, which will be many, many times more than the valueless derived from the inner galaxy. And we think the dark matter halo extends far beyond the sun's orbit around the galactic center. And here's an artist's impression of what we think is happening. The sun is somewhere buried in the galaxy, and around it, probably even further out than this, is a dark matter halo. Here it's a pale blue matter halo, but just to indicate, this is an artist's impression. And the final exercise is, here's a schematic of the dark matter halo. Here's a galaxy. We think it may be very much bigger than the galaxy. The question is, in a spherically symmetric dark matter halo, how much the average mass density varies a function of R to account for the fact that the rotation curve is flat well beyond the stars. So it's just a little exercise in Newtonian gravity. How much must the average mass density in the dark matter halo vary as a function of R? It's not exactly what happens, it's a slightly more complicated function, but it gives you the right idea. So a PDF of these exercises can be downloaded from the eSeminar page on the DARA website. Look at the announcement of today's talk and click on this exercises to complete after the live session. So some of you will enjoy doing those, I'm sure. Okay, well, that's it. I'll see you again for eSeminar 2, when we are going to actually go through using the TTRT in my back garden. I've propped it up on the little table here. and hopefully have a slightly better apparatus than that. But fundamentally, the TTRT is this, with the electronics box, a little dongle which does the digital digitization of the signal, and some programs on PC which you have to supply. Okay, that's it. So see you again for seminar 2, but first, any questions?
Okay, thanks very much, Peter, for taking through the background of all the things that people will be able to do when this kit arrives in Africa and people can start to make the measurements themselves. That's absolutely fantastic, so that people will understand the background, and it's always good to set some homework, keep people active, and actually interact with the data as you've set out. So I would encourage everyone to have a go at the exercises. This certainly takes me back to a few things as well. A few years ago, the Leeds group published a press release actually about how many spiral arms the Galaxy had, using again the same artist impression that you've left on the screen there, because we kind of confirmed that kind of picture. We were actually using emission from the carbon monoxide molecule rather than hydrogen to track out the spiral arms, but exactly the same principles and theory. So it was great for me to have a refresher on all of that as well. Okay, so we have a few questions coming in. Let me bring up, try and unmute some people. So I think first question is from one of your Kenyan colleagues, Dennis Kayang. Dennis, hopefully you're okay. You can ask the question yourself. I've unmuted you.
Okay, thank you, Peter, for the presentation. And I think my question came before you explained between the matter distribution, the dark matter distribution, in relation with the differential rotation of the stars. So that's what I wanted to know. What can we deduce from the differential rotation of the stars near the center and outside the galaxy in relation to the dark matter halo? Thank you.
Well, as I was saying, I think it's the matter distribution. It's obvious that you can't have a constant velocity as a function of distance, flat rotation curve, without some additional distributed matter, and it's not in the form of stars and gas, too little of it. So it has to be in this extra distribution of matter, which we can detect gravitationally. So its gravitational effects are imprinted upon the rotation curve, the fact that it's flat, rather than this falling off as a function of distance. There has to be this approximately, the example asks you to work out what its density must be. It's been done in rather more complicated detail than that, as people trace out the rotation curves. It's the very fact at this level, since, as I say, this isn't a research seminar, at this level, it's the very fact that the rotation curve is flat, which tells you that there must be this smoothly distributed, more or less smoothly distributed dark matter halo around us. Interestingly enough, and this isn't being done by radio astronomy, one of the ways of deducing whether it's entirely smooth or whether there are clumps in it, there are some so-called stellar streams in the galaxy, which are the remnants of our galaxy eating other galaxies, tidally stripping the stars. And there are some huge streams across the stars, across the sky, which have been particularly clearly shown by this Gaia satellite. I showed a Gaia picture earlier on. And from little breaks in those streams, people are beginning to try to deduce whether the dark matter halo is entirely smooth or whether it has blobs in it. So you need some sort of diagnostic, and it's the stellar streams mapped by Gaia, which is one of the research areas at the moment.
Yes. Okay, thank you.
So that was a rather long-winded answer, but this is right at the research frontier at the moment, I must say, which is not my particular topic, but I know as much as I've just told you.
Yeah, I appreciate.
Thanks for that, Dennis. Next question was, I'll ask myself on behalf of Solomon. So Solomon's still in Ghana, waiting to come to Leeds for his masters, but he said he had to run off or he's in the middle of preparing a planetarium show. So
well done for him.
Exactly, and so he works at the Ghana Planetarium. So he had a very interesting question. So obviously been reading around the subject a little bit. So he was saying in 1951, Morgan was able to show that the Milky Way had spiral arms, but with a totally different method. They were using the hot O and B type stars and looking at the interstellar reddening and mapping out the H2 regions. So basically finding the distance to H2 regions that way and marking out the spiral arms. Whereas obviously you're looking at the atomic hydrogen gas. So he was wondering, how different was that picture in the 1950s in a sense to what the early radio astronomers were finding, or did they agree?
Well, again, I appreciate that actually people knew some basic aspects of galactic structure in the first half of the 20th century, and there are other ways of doing it other than hydrogen. Hydrogen, of course, sees all the way through the galaxy. So when you're looking at some of these stellar diagnostics, you're always affected by dust. And so you're never absolutely certain, because of the amount of reddening and obscuration, how much of the galaxy you're actually seeing. So you're seeing through a glass darkly, so to speak. So you can clearly, they did pick out the basic structure. And what I would say is that the radio observations took it to a next level. They also, as I was mentioning, have one of the problems is the distance ambiguities, and hence a very good way of doing it, or Melvin's mentioned another way, is this VLBI method. That's right up to date, where you can get the distances to to mazes around hot forming stars exactly, and see the spiral arms more clearly. But it's been a continuous sort of struggle through the fact that you're seeing inside the galaxy and into it, rather than this beautiful picture that's on the screen at the moment right from above. So as usual in science, every step adds to the previous step. And I'm not saying that by any means that the hydrogen picture of the galaxy is the final word, because of the complications of distances and non-circular motions. But it is a very important, was a very important milestone in the development of galactic science and in the development of radio astronomy, that radio astronomers made people sit up and take notice. Gosh, because remember in the 1950s, astronomy was still very much optically dominated. And this map, I think, made people sit up and take notice that radio astronomers are there to be respected.
Indeed. And I think, as you sort of alluded to there is this kind of constant toing and froing between the different distant methods and rotation curve methods. And I mean, maybe I could follow that up myself a little bit with...
Please do.
Now that we have, this developing quite accurate sort of picture of the spiral arms from the mesoparallax people, you can then use that to refine the rotation curve, of course, in detail. And maybe, I don't know if anyone's done it yet, but to go back and sort of now redo the mapping of the hydrogen map from velocity to sort of XY space, as it were, and do a new version, or and compare it to other markers of the spiral arms. I don't know, actually.
I don't know. Well, as I say, I'm not completely up to speed with that. Of course, the H14 pi people have done this fantastic map of the sky. I'm sure there will be many products of that coming out in the next few years. They've shown the picture, that they've got the basic done all the basic data collection. I imagine there'll be a myriad of papers coming out interpreting the basic data, but I don't know at the moment.
Yeah, no, I mean, at some point we should get to the accuracy where we can dissect structure across the spiral arms, because you expect, sort of H1 to then transform into the molecular clouds, and then them to transform into the stars in the H2 region. So there should be a little bit of spatial separation there, but I think it'll take a while before we've got that level of detail, I think. But, and of course, the Gaia satellite itself is building this fantastic 3D model from the stars themselves. And so linking all of these different 3D pictures together is going to be very interesting, I think, in the future. And of course, bringing it back to the SKA and the AVN actually in particular, because one of the best science cases for the AVN really is to be able to do these maser parallaxes for a lot of sources in the southern hemisphere, which we still
indeed. That's one of the points they were making from that picture of the maser parallaxes. Is principally done from the northern hemisphere. There's a whole half the sky that hasn't been done. No.
So there's a fantastic amount of work to do there. I notice Solomon is still on. I can just unmute him. Let's see if did that answer your question, Solomon, or do you want to follow up? Or he might just be gone away and being busy. Okay, it's not coming on. Okay, so we have a couple more questions. So the next one is from Alex. Alex, would you like to go ahead and ask your question? I've allowed you to unmute. Yeah.
Okay. I wanted to know if the TTRT can be used to measure other nearby galaxies, like NGC 318 and so forth.
I think no, but I'm just hesitating slightly, because the answer is fundamentally no. Not that in principle you couldn't do, if I was able to move the telescope around and track the sky. At Jodrell Bank we have a telescope called the 7-meter telescope. It's actually 6.4 meters across 21 feet, and with that you can easily see, rather similar, a little bit bigger than the telescope we saw in that video. You can easily see the galaxies Andromeda and M33, which are particularly M33, very easily. Now, they the way you could see that you got them, particularly M33, is that there are different velocities, different radial velocities to the Milky Way hydrogen. So if one was able, even with this little telescope here, if you were able to sit and track it for, I don't know, 12 hours or more, you would spot a little blip at a frequency, a radial velocity, which couldn't be coming from the galaxy. So the answer is in two prongs. One, no. Two, yes, in principle.
Okay.
But it is very painful. But the beauty about the hydrogen is that the velocity is a great diagnostic. So you could see M33. M31 gets a bit confused. Part of M31 has the same velocity as part of the hydrogen velocity, but you could probably see M31 and M33, but only if it was sitting on for example, on an optical telescope mount that could. So that's an interesting idea. That's an interesting idea. This is a very light thing. It only weighs the little cone and tin can there. Probably only weighs, well, less than 2 kilograms.
Okay.
The kilogram-ish thing. So if it was mounted on an optical telescope mount that could drive around, then it'd be interesting to see the enterprising students who got hold of the kit could point it at one or two nearby galaxies. If you could see, and of course M31 is not so, they're a little bit in the north, but it may be possible to point out one or two nearby galaxies and see whether you could see them with a long integration.
Oh, okay. Thanks.
Yeah, well, talking of enterprising students, I think you basically answered Andrew's question, but I'll unmute Andrew's, and I don't know if Andrews, you want to comment on that? You asked about mounting of the telescope, which I think has just been addressed, but do you want to comment, Andrews?
Yeah. Hello?
Yeah,
Hello, yes. Hi, Andrews.
Okay, good day. Nice presentation. Yeah, my question was about, I could see that there's no mount, no way of moving the telescope, so I was asking whether there are plans to get a mount for it, or...
Very good question. Very good question. Sorry for it. Absolutely pertinent question, Andrews. So I haven't done that yet, but what's going to happen, because it's the whole point of this is it's a tabletop radio telescope that is easy to use. So we're not going to have some complicated electronic mount. The idea is, and again, I've been held up by coronavirus, so I couldn't get this done at Jodrell. This is informally mounted with a little table, with a little stool underneath it. The scheme is that it will be mounted on a piece of wood, which will be supplied, with a little notch at the end to hold it in place. And then the telescope itself will have some steel wires, I suppose, bits of steel, not cable, but anyway, holding it up. I'm going to be able to hold it up, as you can see me, like that, with some wires coming down like that. And this is going to have a piece of wood which the wires can plug into, or the stanchions, if you like, can plug into at 5-degree elevation intervals. So the elevation is going to be movable at 5-degree points. This is all done with a piece of wood and some wire to make it cheap. And then you can move this wire on the piece of wood on your tabletop in azimuth just by moving it around. And you can measure the position, because the beam is quite big, you can measure the position using a mobile phone. So you can get the correct azimuth with a mobile phone easily. Any app will do that. And you can get the correct elevation with a mobile phone. Lots of apps will tell you what the tilt angle is. And you're going to get and this will all come in the e-seminar too, of course, you're going to get a little piece of software that enables you to convert from where you are, what time of day it is, and where in the galaxy you want to point, to an azimuth and elevation, which you can set up on your telescope. And because the beam is quite big, getting it right to within a few degrees, even 5 degrees, is quite good enough. So the whole point is cheap and not easy to break, because I want this kit to last for many years. And if you have something which is too sophisticated, well, it has a chance of breaking. This is supposed to be very, very robust. So the principal pointing apparatus is simple. It's a tabletop piece of wood and some little pegs in the board. And with that, you can point it to a few degrees quite accurately, quite easily, with a mobile phone. If you could then, if some enterprising student wished to mount it on something more sophisticated, well, that will be excellent. But you'll be surprised with something simple to get going with. Simplicity has been my watchword in this whole experiment. fundamentally, I've found that students are really very excited to see hydrogen for the first time. Then if you point it in a different direction in the galaxy and see hydrogen at a different velocity and you've detected the galaxy is moving, is often, well, not necessarily good enough, but often is a real thrill.
Okay.
Yep, indeed. Nothing like first-hand stuff. Alex, you have your hand up. Did you want to come back?
Yeah, I was just thinking aloud. I think at GSSTI we have this ASTT, this telescope, which is supposed to be used for demonstration to students, which is a bit steerable. So you could give some coordinate and it will move to those coordinates. I'm just wondering how maybe we could in interface. I don't know the electronics for this telescope. If we could somehow integrate the two, because that could move. I mean, you could point into any direction you want. So I'm just looking at if there's a way we could say sort of replicate the TTRT together with that to see, because I don't know specifically what electronics here helps in measuring the H1 signal, or perhaps if you could just take a normal say normal maybe 5 centimeter is it 5 centimeter or 5 meter DSTV dish, if it is steerable, if you could move around, would it work the same, or is there something peculiar about TTRT that makes it be able to measure H1 signal?
No. So the size of these are satellite dishes, are they?
Yeah, because that
How
one
big?
with the mounted LNA and stuff.
Yeah. Well, all that in the little gray box here.
Yeah.
This is just an antenna with a wire. That's just an antenna.
Okay.
In here are some really quite nice low noise amplifiers and a really quite nice filter. So all that is in here is 2 amplifiers, nice amplifiers. You can buy commercially, but they're very good performance, and a filter to filter out the main problem is mobile phones.
Okay.
And then this here,
yeah,
the little dongle is costs about £15 or about $20. So all we would need to do, and maybe this, if next time we come to Unit 2-3 in Ghana, this would be an interesting thing to explore further. All you need is this box, really,
okay,
and that dongle.
Okay.
Of course, you can do it much more sophisticatedly, but with a much more sophisticated back end for hydrogen observations, as we saw in that video.
Yeah.
But keeping things simple is a very good idea, and you could make more sophisticated observations with a 3-meter telescope or a 5-meter telescope just using the same kit.
Okay.
That would be an interesting thing to explore. But it's best done on the ground, so to speak.
Okay.
That would be very good. That would be very good.
Yeah,
you would certainly. Sorry, just to interrupt again. You would certainly see some nearby galaxies with that.
Okay.
Yeah, we've got a few more questions that are probably preempting the second part of your e-seminar, but let's give people a taster. So, Simon, do you want to ask your question, please?
Hello. I think, okay, thank you for the presentation. I think part of my question has been asked by Alexander, because I was wondering whether you've designed it in such a way that the student can improve on it. And I think, and then the other part was on whether you've used commercial off-the-shelf components. And I think you've already answered those parts.
Yes, I think the improvement would only be mainly be in pointing it more accurately.
Okay.
And enabling it to track things. And then if you could do that, then you could, for example, study the relative amount of hydrogen at different points, say away from the galactic plane where the amount of hydrogen is less. But it's an interesting point that you make, improving the apparatus. You can't improve its sensitivity. It's already sensitive enough. Not sensitive enough, it's always as sensitive as much as it can be, given the size of the horn there. You could make a bigger horn. You could certainly make a bigger horn to fit on the, you can buy those actually, but you could, this horn, by the way, the bit at the end, the slightly gray part, is part of air conditioning. And air conditioning equipment goes from a certain size to a certain other size. And it turns out that one of the air conditioning duct changing bits, so to speak, is a perfect horn like that, which fits on almost exactly onto this tin can here. So you can make a bigger one of those. People have shown you how to do it. You could double the size, for example, and that wouldn't damage the apparatus, or you could point it. But the amplifiers and everything else inside is commercial, except the filter, which I've got specially from a friend of mine who supplied them to us quite cheaply, because the major enemy in this is mobile phone transmissions, which are in fact a long way away from the hydrogen line. They're about 950 megahertz and 1800 megahertz, but they're so strong that they can get through the apparatus and mess up the dongle. So you have to filter them out very, very carefully to get good results. So the main difficulty is getting that nice filter. I've particularly got one from a friend of ours who built them at, I think they cost about £70, which is incredibly cheap actually. They're very, very good. We may be able to source them from China, in which case it could even be cheaper, but I've got 20 of these nice filters. That's all inside that little box there. And the dongle itself is freely available and costs about £15.
Okay. Yep. Thanks for that. Seyram, do you want to ask your question?
Yeah, yes, sir. Hi, everyone. I wanted to know if you have a photograph of the image of the TTRT telescope.
So I didn't get that. Can you just say that again?
Yeah, I said I want to know if you have an image of the TTRT or a photograph of the output of the TTRT telescope.
I don't have a picture of that exact output, but I have pictures of outputs of similar type things I've done with previous. Because this is it's a good question. I've built on. This is built upon experience of several sets of students doing precursor experiments and teaching us what not to do and what to do. So the answer is no, but I have something very similar to it. But I can't put it up on the screen just at the moment. They're not as good. I mean, the point is that the beam of these telescopes, the beam width is much bigger. So the beam width of this telescope is about 30 degrees. Whereas the beam width of that lovely little French telescope in the back garden was probably about 3 degrees. So the spectra tend to be much more blurred. So it's much harder to see the individual spiral arms with this. What you can see is the overall rotation. You can see that as you point in different parts of the galactic plane, you'll see that the peak of the spectrum shifts around. And then you'll also be able to see that away from the plane, there's far less hydrogen, and you'll be able to see approximately what the ratio is. But the main point is the spectra taken with this telescope will be more smooth, just because the beam is bigger and it gathers together hydrogen from a much wider range of angles. That's why I supplied for the exercises spectra taken with professional radio telescopes to show you what research level or close to research level spectra look like. But this is to fundamentally, the point of this experiment is to excite students who may become DARA students, plus some DARA students, but to excite some undergraduates to get into radio astronomy, and not to confuse them too much with no, that's the wrong idea. To let them see that they can, from their own back garden or from their own university back garden, and in the daytime. The beauty about this experiment, of course, is you can do it in the daytime. You can actually see the galaxy, the invisible galaxy, and you can see it rotating.
Yeah, I think that is probably on Patrick's mind. So Patrick has the next question. Patrick, do you want to ask your question?
My question was, first of all, thank you, Professor, for your presentation. It was very wonderful. I'd like to know the software which is used to connect the telescope to the computer or the mobile phone. Thank you.
Okay, thanks, Patrick. The mobile phone isn't involved. The mobile phone is only used to, will be used, which everybody will have, to point the telescope, to point it in azimuth and elevation. The software, well, the software to tell you which azimuth and elevation to do, to point at, will be supplied as a little app on your PC. That's all going to be supplied on a stick, all the software. So the conversion from galactic coordinates to azimuth and elevation for wherever you are on the Earth for time of day. I had a summer student under my supervision last year, and that works very nicely. So that's easy. So with your mobile phone, you'll be able to position the telescope. The software for taking the data from the little dongle here, which is the digitizer, amplifier and digitizer, has been written by other people. A good colleague, an amateur radio astronomer who's really a professional radio astronomer. He used to be the chief technical officer for a major UK radar company. On his retirement, he decided to take up amateur radio astronomy. So in fact, I have used his software largely, changed slightly, but that is all supplied for you. And that takes the output from the dongle, and as explained in great detail in the instruction book, that enables you to take data and obtain spectra. One of the things I wanted to do with this TTRT, as I'll explain, is it's not just, oh, point it up there and you can see something. No, you actually have to go through a set of observational protocols. Quite simple, but you actually have to point it, calibrate it. It's explained exactly how to do that, and then use the calibration to bring up the spectrum. So it's not just a point it and there's the spectrum. No, you have to go through a radio astronomy process. Relatively simple, but nevertheless, you have to go through a process. You've got to win the spectrum. You're not just given it. But that software will all be supplied on a pen drive in the little box it comes.
Yep, jolly good.
But you do need to supply a PC. The only thing you have to supply, as you can see here, is power lead. In Kenya, of course, it's very good. The plug connector there is exactly the same in the UK. So that's for 240 volts. That's a little transformer there, plugs into here with 5 volts coming in here. So this is 5 volts coming in here. And that powers everything. So you need to have, you can take this anywhere, but you do need a supply of 240 volts. That's all you need.
Okay, yeah, I'm sure we'll hear more details in part 2. And finally, we knew this question would come up. Francis, do you want to ask your question?
Thank you, Prof. Please, I would like to know how much this nice, wonderful telescope will cost. It would be nice to have one in my university.
Yeah, well, I mean, what I will do, because DARA is going to supply 20 of these, and where they go to is to be decided by our esteemed principal investigator, who is in charge of this this seminar. But what I can easily do is to supply the full details of what we've done. Then you can make it yourself, because you can get hold of the can, you can get hold of the details of how to drill the hole in the can. All that is very well known. This has all been done before. I've put it together in hopefully in a very self-consistent way. But the total cost of this, and it depends upon whether you could get a filter from China, because the filter is one of the most expensive parts. But it probably costs, it's a few $100s or a few £100, maybe 200 minimum. Okay. So sort of, the cost of the antenna is almost nothing, or maybe 10, 20 pounds. The little grey box there contains some very nice amplifiers and a nice filter. That's probably £200. It might be possible to do it more cheaply, but the best thing to do is to do it very well, and it's incredibly reliable. And the cost of this little dongle here is about £15. But forewarned with that, I will be, when we come to doing seminar 2, I'll put up the costs on the screen as to what I've paid for it, and see whether we could do it any cheaper than that.
Okay, thank you.
Yeah, a list of costs and a list of typical suppliers might be good, and people can do their own thing. Okay, maybe a final question. Sigrid, do you want to ask something?
Hi, yes, thank you very much. Thank you, Prof, for your presentation. I think I want to hear more, actually. Very excited. I'm a student, and I would really, really want to be part of carrying out this experiment as well. I just want to find out, well, I had a couple of questions that I know Mervyn have asked already, that this TTRT can actually detect or pick up how many spiral arms the Milky Way have. And also, I think Alex has also touched on the one question that I wanted to ask: how easy is it to upgrade the TTRT? But now I would just like to find out, since that all those questions were answered, I want to find out how quick can we get hold of this TTRT?
Well, we've been held up by COVID-19. This is my prototype, which I just want to test. I still haven't tested it in the garden yet, because we've been having a bit of problem with cables. I've shown it cabled up here, but I don't trust this cable because I can't get into Jodrell Bank. So it will unfortunately not be until 2021 sometime. I mean, what the scheme was this year, but of course been messed up by COVID-19, was that we would take this prototype out to Ghana for units 2 and 3, get people to use it, find out all the things that we need to improve with it, or find out what was good, what was bad. Hopefully it's all good, but no doubt when students actually get to use it, it won't be, there'll be something I could do better. So before making 20 of them, I wanted to test it out with a group of DARA students, and to see perhaps that the hardware was all okay, but that the explanation in the book could be improved. So I didn't really want to produce the full set of 20 until we were convinced that the prototype did exactly what we wanted. So it'll be, and so we couldn't go to units 2 and 3 in Ghana in April, May. So I'm set at home at the moment, unable to go into Jodrell Bank. So it will be slowed down. It will unfortunately not be till next year. So one thing you can do to improve it would be to make the horn bigger. I think with a piece of aluminium shaped correctly and wrapped around the existing horn, you could at least double the size of the aperture. And that would work without doing any further clever radio frequency testing. That would make the aperture 4 times bigger. So you could certainly make it into a bigger aperture, and therefore make it more possibly easier to see some spiral arms, because that is just a question of resolution, angular resolution. It's not a question of sensitivity. It's easily sensitive enough. It just needs to be bigger. I could imagine a year from now, various versions of larger horns being put together across Africa. Maybe could be done with plastic, with kitchen foil stuck to it. I can imagine all cheap ways of making a bigger horn. I think that would be the interesting way to make it more sensitive.
Okay, great. Now I'm more excited that you mentioned that you wanted to actually test it out with the DARA students at, I guess you are talking about the basic training, right? Unit
basic training, units 2 and 3. That was going to be the so-called acid test as to, it's all very well doing it here. Although I have used students, this is based upon student work in the past, but the exact apparatus here is new. So you have to test it out with real students, because as all lecturers and academics and teachers know, once you put it in front of students, they find ways not to break it, but to find ways to use it that you didn't anticipate. So
can this acid test also take place in South Africa for units 2 and 3?
Well, that would be good. I mean, by 2021, next units 2 and 3, perhaps we can make 2 of them. We should send 2 of them out, and it would be good. It would be good to. This is a very good point. It would be good to have one run by me in units 2 and 3 Ghana, whereas I was going to go. I don't intend to go to 2 places, but have the other one run possibly with a Zoom link as well, with advice from me over a Zoom link in Africa, in South Africa. That would be a good idea to get 2 of them going, and see how easy it is actually to use remotely with some guidance with a Zoom link.
I was just thinking of that myself as you were talking, and so yeah, good that you suggested that, Sigrid, because that's exactly what I was thinking as well. So we'll
thank you.
We'll try and persuade Peter to make a couple, and then we can.
I think that's a very good idea. I think I can definitely agree to do that.
Yeah, great.
Not agree, but I think that would be a good idea to get one for South Africa. And even though I wouldn't go there, I could still be available by Zoom. And actually, that's 90% of the battle.
Yeah, and I think we'll be sending someone out from the UK anyway, and so I'm sure you can probably train them up before they go. So that should work.
Okay, good.
And they can obviously take the kit with them as well, which is another point. Okay, Peter, would you like to stop sharing your screen? I think maybe, and I'll just wrap up. So again, many thanks to everyone for their excellent questions. A really good set of questions, and you can see that I think people are very keen to look forward to the next part of this to get a better idea of how the kit works, how to put it together, and how to operate it. So that we look forward to that. Maybe I'll hand over to Trish just to talk about upcoming seminars, perhaps?
Yes, thank you, Melvin. So firstly, thank you, Peter, for giving such a great talk, and we look forward to part 2.
I'm sorry about the audio.
No, it's okay. It was working and then it wasn't, but that's absolutely fine. And thank you to everybody for attending. I will be sending out, as usual, emails to request feedback. So there'll be a link in the email. So please feedback and use it as an opportunity to put forward suggestions. We are still scheduling these for the next 6 months, I could imagine, at least, and if not longer than that. Future seminars that we've got planned, we haven't got dates for them just yet. We have one from Roger Dean from the University of Pretoria, and he'll be doing his talk on the first image of the black hole. And we have another one planned from Rod Hine from the University of Leeds. And Melvin, I'll pass to you again just to summarise what we hope Rod will be talking about.
Well, like I said, along very similar lines to Peter, I'd be talking about sort of amateur radio work, not necessarily amateur radio astronomy, but you know, building amateur radio kit to talk to people across the world and that kind of thing.
Great. So we're hoping again to continue with 2 seminars a month. We do have quite a few lined up. We just need to get those scheduled in. Also to let you know that the last e-seminar by Carla Sharp, that's now available on our YouTube channel. So please have a look at that and also subscribe so you'll receive notifications when we do add new content there. I think that's everything really from me and nothing further to add, so I'll pass back to Melvin to close.
Well, maybe this is probably the wrong audience to ask because obviously you're here and attending this seminar, but we had a suggestion from one of the regular participants that maybe this, you know, a lot of people are getting back to work now across Africa and have to go back to their day jobs, and so the timing here in the middle of the day was not so convenient for them if they're going out to work. Again, if people want to perhaps in the feedback comment on that, you know, if we moved the seminar time to sort of early evening, sort of just after work hours or something like that, if people think that would make it easier for people to attend, or of course it might make it harder for some people to attend, so we don't want to do that either. Obviously the recordings are available for everyone at any time of their convenience, but of course if you want to get involved in the live Q&A then you have to be on this session. So, you know, have a think about that. So yeah, just remains for me to, you know, thank Peter once again for a very illuminating talk. You know, you can see the years of experience and everything coming in there. That's really fantastic. And obviously thanks, you know, for doing all the work with generating the TTRT as it is to date. So thanks everyone, and we'll look forward to seeing you on the next one. Cheerio.